As AI becomes more commonplace in our lives, the challenge presents itself to be able to explain how these algorithms work. In particular, we need to know why a model makes the predictions that it does. This knowledge is critical in regulated industries such as finance and healthcare. To this end, here I'm going to experiment with two different approaches for global model explainability. These include summed SHAP values and SAGE. First, we will briefly touch upon the distinction between local and global model explainability, and then afterwards jump into a notebook to cover the actual experiment. All coding shown in this video is done in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. So let's talk about what do we mean exactly by global model explainability. So it actually turns out that there's two different approaches for trying to explain how an AI model works. You have local explainability. And this is the situation where we are interested in explaining how a model arrives at a specific prediction. So say if we have a classifier and this classifier spits out a certain value, we may be interested in why the model actually made that specific prediction. This can be important if, say, we're trying to justify why the model performed the way that it did to, say, certain regulators or compliance officers in the specific industry that we're in. So this is what we mean by local model explainability. And there's already a very popular Python library that is suited for this task, and that is SHAP. Now, SHAP has been around for a few years, and it is specifically tailored towards local model explainability. Now, what do we mean by global model explainability? Well, in this scenario, we're not interested in explaining why a model arrived at a specific prediction, but what drives the model overall over an entire data set to make the predictions that it does. So this is operating at a higher level. We are trying to understand why the model behaves the way it does over an entire data set, or more broadly, over the entire data generation process. So this is what we mean by global model explainability. And this is very important, specifically when we're talking about model validation. This is typically something that is done, or that is required. So we have one common approach for achieving this is to just compute the SHAP values for each individual sample in our data set, and then we can sum the absolute values of those SHAP values. So that's what I'm going to term here as just summed SHAP values. Now that's one simple approach, but it's not very rigorous in terms of achieving global model explainability. In contrast, we also have SAGE, and this is a more recent algorithm. It stands for Shapley Additive Global Importance. And this algorithm is specifically designed to treat for global model explainability. Specifically, we are trying to figure out which features drive the model towards better or worse performance. So these are the two different approaches that we are going to take for looking at global model explainability and the different pros and cons that we can get with either approach. So now we're in a Jupyter notebook, and we will start off with importing all the packages that we'll need for this experiment. So we can do that just by running this first cell here. You'll notice that I am importing also the packages SHAP and SAGE. So those have also been installed in my local virtual environment. So we can go ahead and run this cell. Okay, so the data set that I'm going to use here is going to be just a very simple toy regression data set. And the objective here is just to illustrate some of the properties for either of the approaches that we're going to look at for global model explainability. So specifically, what I'm going to do here is generate a data set of 10,000 samples. I'm going to fix the random state so that we have reproducible results. And I'm going to produce 3 different features. So we can see that here, each normally distributed. And I'm going to establish a linear relationship between 2 of the features, so that's x1 and x2, with our target y. So this is the setup that we're going to have, and then I'm just introducing a little bit of noise as well in the output. And then we can just package up our 3 different features, and then do finally a train test split, where 20% of the data is being held out for testing. So it's important to notice here that we've got a linear relationship, and in fact only 2 of the 3 features are important. Notice that x3 is not relevant for y whatsoever. So this is going to be our data set. We can run the cell to generate these data. And now let's just quickly visualize the results that we've got. Okay, here we see the 3 different features, and they're all color-coded. So feature x1 is in blue, and we see here it's just poking out at the back, and it's somewhat elongated. Then we've got feature x2, and that is strongly elongated, that's in orange. And then we have x3, and that's symmetrical about x0, so about the 0 point in our horizontal axis. And this indicates that, yeah, there's no relationship between x3 and our target, the fact that it's just completely symmetrical in this plot. On the vertical, yeah, we have it labeled here, that's our target. So okay, these are our data. This looks pretty good. Now we can go about to actually trying to model this data set. And just to be complete, I'm trying two very different regression models. So the first is going to be a random forest regressor. This is an ensemble of trees. And then I'm going to also try a linear regression. So, we'll try out both of these models to see how they perform on the data. So let's just run this cell. We're going to create our model, train it, and then also measure the root mean squared error on the test set. And here we can see the results. And we actually notice that the linear regression does a bit better than the random forest. And this is not too surprising because, after all, we know that these data in reality have a linear relationship. So it kind of makes sense that the linear regression should do pretty well. Now let's dive into our actual experiment, which is trying to achieve global model explainability. Now, to make things a bit interesting here, what we're going to do is on our test set, we're going to actually reverse the sign for all the samples of x2. And the reason for this is because we want to experiment, we want to try out what happens when a feature is actually driving a model towards making mistakes. So let's think about this for a second. Our models have been trained on the training data, which has this nice linear relationship. The models are trained expecting this behavior. And now we're going to test these models on a test set, but where x2 has its sign flipped. So the consequence of this is going to be that x2 is going to drive the model towards making mistakes. So let's see what happens with our two different approaches with this entire setup. So we can run this cell to flip the sign. And now the first approach we're going to take is with SHAP. So again, what we're going to do is we're going to set up a SHAP explainer for both the linear regression and random forest, and that's what we're doing in this first code block. And then below, what we do is we are going to aggregate the SHAP values that we get from these approaches. We're going to take the absolute values so the signs don't cancel out between individual samples. And then we're going to basically record the summed result that we have. And of course, we're going to also time this whole process to see how long does it take to achieve all of this. So let's kick off this cell. Okay, this finished, and it actually didn't take that long. The wall time is 24 seconds, and we've got our results. So okay, we now have our SHAP values. Let's try our alternative, which is SAGE. Now with SAGE, what we have to do is set up imputers for the data that we're going to try and test. And then afterwards, with those imputers, we set up our estimators. So here we've just got two permutation estimators for each respective model. And then with each estimator, we then obtain our SAGE values. And those SAGE values should represent how influential each individual feature is over the entire data set. So let's compute these now. Okay, this finished running. It did take quite a bit longer. So the wall time here is 1 minute, 28 seconds. This is quite a bit longer than the summed SHAP approach. But yeah, that's the first point of comparison that we can see. Now let's actually print out the values that we get to see what kind of results we have. So here we've got the SHAP and SAGE values for the linear regression. And now we have the same thing, but for the random forest. Okay, so then looking at this and the timings that we recorded already above, we can make some conclusions. So the first point is that the choice of model, at least for this particular data set, didn't really have a big impact. We see that both the SHAP values and SAGE values kind of remain consistent, whether we're using a linear regression or random forest. So there isn't much of a distinction between these two iterations. Now, both approaches show that X1 and X2 are both informative. And we see that because both of these values here, so for both SHAP and SAGE, and we see it in both linear regression and random forest, they're far from zero. So they're substantial numbers, whereas for X3, both results return very small numbers close to zero. So both manage to detect that X3 is not important for this model. So that's the first thing that we can pick out. Now, one important thing that we do see here, though, is that SHAP, the summed SHAP approach, is not able to discern that X2 is actually driving the model to make mistakes, whereas SAGE is. And we see that because SAGE has this large negative value. For the linear regression, it's minus 27, and for the random forest, it's minus 25. For the summed SHAP values, all that it's able to record is whether a feature is influential to the output or not. It doesn't measure if that feature is actually driving the model towards better performance or not. So it's a key distinction between the SHAP approach and SAGE. So in fact, with with using just SHAP values, we have no idea of knowing whether these features are actually making a positive contribution or not. So this is a very key distinction, and it's a critical one for this experiment, that if we're really interested in knowing which features are improving our model, SAGE is the way to go. So that's a key thing. Now, of course, there's a downside to SAGE, and that it comes with our computational time. So we saw above the different wall times. Computing with SAGE, at least for this experiment, was roughly 4 times longer than just doing the summed SHAP values. So that can represent some challenges for actually making this implementation work. So this concludes the video. I hope you enjoyed this and learned something from it. If you like this content, please like and share the video, and please subscribe to the channel. It's always appreciated to have your support. So that's all for now. I hope you have a great day, and see you in the next video.